Okay, we set the goal then, Aaron, I think. Okay, so want to welcome everyone to this session on principled item design. I just wanted to say, rather quickly, Isaac and I started talking about this type of a session about 2 years ago. I think it was Isaac, probably even earlier. And so we were very honored to get together the speakers that we have. And so we've got the 5 speakers. I'll let everyone introduce themselves as they speak. And then we're going to ask, if you have any questions, please put them into the chat room. There's a chat button at the bottom of your Zoom screen. And time allowing, we'll address those at the end. So we also have Steve Ferreira as our discussant. So there'll actually be 6 total presenters there. So Susan, I'm going to let you unmute yourself, share your screen, and you're on.
Okay. Hopefully everybody can see this. This is my title screen. I'm going to look at, yes, good. Item and test and item development with cognitive design systems. Some examples. And let me introduce myself too. I'm Susan Embertson from the Georgia Institute of Technology. Understanding cognitive complexity in items has some important implications for the prediction of item difficulty, to design the test to have specific difficulty sources, to support construct validity, that is the response processes aspect, and in terms of empirical tryout, that is, having the models may lead to a reduced need for empirical tryouts of items, particularly if coupled with automatic item generation. Let me define item generation. You're all familiar, but let me do it anyway. Of course, this involves the algorithmic and typically computerized substitution of item content into structures. Now, the structures might be based on an item model, that is an existing item that has been variabilized, or it can be based on an abstract structural representation. So the item generation components then are the structure, however it is defined, and then content sampling principles, where you have databases and certain constraints depending on the item. Let me take 2 extreme examples of what the item development process is like. In the traditional process of test development, item design is not well specified. Item writers are told to make some items, kind of like some other items. And so they do, but those items then are going to be submitted to a full content review, a full empirical tryout, and a full empirical calibration. That's the traditional way of doing it. Now here's the extreme on the other end of an expedited process. Items are generated on the fly. There's no content review, but of course there needs to be a previous review of item structures and databases. No empirical tryout, that is, items from the same structures or model have been tried out previously, but not necessarily this particular item, and no empirical calibration. Item parameters are based on predictions that have been developed in advance. So this is very extreme difference of a test and item development process. Now, let's look a little bit at defining things here. Item structures. Well, we have family variants, that is, they're generated to have the same parameters. So you have a calibrated structure, really, based on a few items that have been generated from that structure. And then, of course, you make predictions from new items based on being a member of that family of generated items. So you have the same parameter for family members. cognitive model, what do I mean by that? Well, predictors based on scored features of the item structures themselves are what's going to define a cognitive model of the structure. And I'm going to show two different kinds of examples of that. And this is useful, of course, if you have some structures that you have not observed yet. In other words, if you have a cognitive model that seems to predict the difficulty in general of a bunch of structures, you might apply that to an unobserved structure where you can score the variables, but you don't have data yet to predict how that structure's item difficulty and item discrimination, if relevant, should be. Also, of course, a cognitive model is useful for test design. That is, what sources of cognitive complexity do you want to represent? So now I'm going to do two quick examples of the two different approaches, the item model approach and variabilization. And I know all the presenters have seen this before, but here's a typical kind of math item. And the person, of course, has to read it and figure out which of these four response alternatives would be relevant. Here's a variabilized version of it. And so you've got different kinds of variables. Garage sale is an X variable, kind of a area or content. S1 and S2, etc., are names. And then, of course, we have the N variables, which are numbers. And those all can be changed. And so you see the same thing on the response options, where we have the different numbers. So this creates a structure then where we can sample content and numbers into the different areas of this item. A very abstract structure is what I have used for my abstract reasoning test. It's a matrix completion type of test. And so you have to figure out what relationships are going on in this matrix and select a response option. Now, I'm defining as my database objects and properties of objects, and those things are sampled. So in this particular item, object A is the diamond shape, B is the arrow shape, and the properties, A1 property is the border on that diamond shape, A2 is the girth, for B, it's the fill. And here's the structure. You see, this is very formal. I can sample all kinds of different objects for A. It doesn't have to be a diamond for A. It doesn't have to be an arrow for B. Can sample that, and also I can sample all kinds of properties. But what's important about the structure is how the properties are related. And so you see that property 1 and 2 for A are going across the screen here. But then we have a structure based on a particular kind of relationship, but that we can talk about later. But you can see that what needs to be in each of these areas in terms of the defined objects and the defined properties is specified. Now the cognitive model is scored from the structure, basically. First, I'm going to look at math items, and there I've used the item model approach and taking a good item from an operational test and turning it into an item model with variabilization. And so with mathematical achievement, these tests are basically pretty high stakes because it's accountability for states, districts, schools, teachers, students, and so on. And so, of course, there's issues. Do the designated skills and items explain item difficulty? Second issue is, do items differ in cognitive process complexity? And do items with the same intended skills still differ in process complexity? Okay, so those are kind of things you could answer with cognitive model approach. So here's the defined skills from a blueprint for an actual test that was developed for grade 7. You can see it has 4 areas: number, algebra, geometry, and data. And those are subdivided into 2 regions, and there's further subdivisions depending on the particular area. And then at the very bottom would be items that would meet the definitions down that stream. And so that's a definition, and there's a representation in the test as a whole of those particular skills. What about a cognitive model? Well, there's been a mathematic problem-solving models. Mayer proposed one, and I've used that in some research subsequently. And he proposes that there's a translation phase, an integration phase, solution planning, or 1 and 2, and finally decision. And what I did is to define variables that drive those processes. We did that first in 2008. Now, let me take an example of a study. We have a year-end test, and it has quite a few items, 84 multiple choice items. They represent that blueprint I showed. And the sample I have was a random sample of 4,000. The cognitive model, as we defined it, had 14 different variables. They go, of course, with the different processes. And the skills, that hierarchical model, at the bottom level, there was 33 different indicators. So this shows you a diagram of the cognitive model. And so we have the translation part, and that has to do with math terms, number of words, reading level. The integration part, and there's several variables there. That is, translate word equations, generate equations, recall equations, etc. And we have solution planning, and then solution execution, all with different kinds of variables defining them. Now, what this means is to do the modeling, cognitive modeling, you're going to have to score all the items for these cognitive variables. And so you can see here an example. Here's the encode math, encode words, encode diagram scores. Also, though, if you want to represent the blueprint, you score that just binary. And so that item 1 involves this first skill, a number skill 1.A1A, and etc. So you score each item for the skill it involves. Now, model comparisons. How well do these models explain item difficulty? And so you can see here the listing of the cognitive variables. And of course, we have the blueprint categories. And results are shown here. I have a fit index. It's kind of like a multiple correlation, but it's based on likelihood ratios. And so the blueprint categories have a fit of 0.698. The cognitive variables by themselves, 0.497, not too bad. Putting them together leads to 0.761. And you can see that it is significant to add the cognitive complexity to the blueprint skills. Now, you can do several things with this. Let me point out that you can use this at the item design level. That is, if you don't want certain areas to be so predominant, You can change the item and you'll have an index to indicate how much item difficulty would change. You'll say you reduced the mathematical encoding or the contextual word encoding and so on like that. I have a subsequent study where I did reduce item difficulty on items. Items were generated with the item model approach. So we had an item model based on an item that had been operational, so it's a good item. And so there's two kinds of items. There's family variants, and those are designed to be similar to the original item model. They have the same parameters. And there's structural variants. There we use the cognitive model to change the actual generating item model to reduce or change complexity in some way. And so we call those structural variants, and then the others are family variants. So we have a study here on grade 7 math items. We've done other grade levels. And so the results show pretty strong prediction from the item models. Now, what we have here on the far right would be the operational items and how they predict item difficulty. The reason why that's in the mix is that the operational items were on 3 different test forms, same items, but in different position. So then I just use the item ID to do the prediction of item difficulty there. So it's predicting difficulty of 3 items. The family variants and the structural variants, these are generated items that were on tryout. And so if items were generated from the same item structure, we have that item structure as a predictor. And so what we can see here, if you look at the multiple R's, which is, I can't even see the operational items because of the way the screen is here, but the multiple correlation is really pretty similar, be it operational items in different positions versus family variants, different content, but the same underlying structure, or structural variants. These are my changed items, but they have the same structure, the same altered structure. You can see that these correlations are all in 90s. So that means we're getting pretty good prediction here. And also, you can see that if you look at the mean item difficulty, you can see that, in fact, the structural variants of items are easier in general. That's what we designed them to do. So that's one example. The other example I'm going to look at is prediction results from abstract structures. And there, of course, we have, as my example, these matrix problems where you have to figure out what comes next in the matrix. Now, don't solve it. So the abstract reasoning test is a measure of fluid intelligence, and I do have an automatic item generator. And I also developed a cognitive model, and there's a prior theory in the mix here, but at the end of the day, I added some things and changed some things from prior theories to get my model. So I have what I call the cognitive model process variables. And there's 2 of them, number of unique elements and memory load. And memory load is kind of a complex variable because it depends on the type of relationships that are in the item. And this is an ordering of relationships 1 to 5 for their difficulty. And so and it's assumed that what an individual does is to try the easy things first and goes on to the 5th one last, you know. And so memory load is just the sum of the levels of the items that are involved. So if it was pairwise progression and distribution of 3, I'd add 2 plus 4 as my memory load. And then we have some perceptual principles that were added because they seem to make a difference. Overlay, fusion, and distortion of elements are something that can create some difficulty as well. All right. So the results, first results I'm going to show you, I've had several results on this, but this particular one was 8
Susan,
items.
can you wrap it up soon?
Yes,
We're getting their time. Okay, thank you.
I thought so. Anyway, I've got 90 generated items, and what we want to see quickly here is the prediction from the linear logistic test model with the cognitive predictors. That fit index is 0.78 with the structures 0.90. So I guess we're getting pretty good prediction. Excellent from structures and pretty good from the cognitive model. This I'll just go by, but this just shows you what is going into the items. And this is another look at the same thing. I'll try to wrap up here. And so, conclusion here. What are the advantages of an empirically plausible cognitive model? First of all, of course, it does support the substantive aspect of construct validity. That's what is involved and how difficult that particular process is in items. We can predict difficulty for new items. Here is an example of predicting the difficulty for new items of the matrix type that I just showed. So you see I've got a prediction there. We also can extend construct validity to the item level. Recall we have processing variables, 2 of them, and perceptual variables, 3 of them. And so we can look at the relative difficulty predicted for the item on those 2 different types of cognitive variables. We can do item banking by source of complexity, processing versus perceptual, for example. And we can do test specifications to control for sources of complexity. And finally, of course, we can do direct prediction of item difficulty and use that parameter in further testing. And that's it.
Great, thank you. So Susan, if you want to just unshare yours, and Isaac, you're up. Okay, Isaac.
Do you see my first screen?
No, I see.
Not quite yet. Did you do a screen share?
Um,
At the bottom.
how about now?
No.
This worked yesterday.
Isaac, when you click on the share screen button, just make sure you're clicking that second share button. Are you seeing that?
Say that again.
When you click on the green share screen button and
Yeah.
select your PowerPoint, just make sure you're clicking that second share button.
Well, Erin, you remember yesterday it worked.
Yes, I can vouch for you.
Okay,
Let me try one more time.
okay,
Maybe
not,
the
we'll
next
switch
person,
to
yeah.
Audra, right?
Why don't Audra go?
Yeah.
I have a little
Okay.
problem here.
Sure. Hi, everybody.
Hi.
Okay, hi, my name is Audra Kosh. I am a research scientist at Edmentum, and I'll be talking today about some things to think about when training subject matter experts to write item models. So it was great to have that introduction by Susan about what item models are. So first, to consider what are the different types of skills needed when doing traditional item development, also referred to earlier at another NCOME session as one at a time item development versus automatic item generation. I think of this as one being a subset of the others. So when you are doing traditional item development, you can see the item in its completed form and think, is this a quality item? What do I need to revise in this item? And you see it all there at once. Of course, this requires content knowledge, best practices in item development, ideally some understanding of psychometric item statistics, particularly if you are revising items according to field test data, and in some cases, some type of editing syntax for content management systems. In automatic item generation, it's a much larger question to ask. You're asking, will every instance of this item generated from this item model be a quality item? So you kind of have to take out your crystal ball and look ahead to all the possible items generated and think, are all of these going to be okay? This is a much harder task, and it requires all of the aforementioned skills in addition to programmatic thinking. So you have to think through what are the possible combinations of features and constraints that generate this pool of items. Deeper content knowledge to account for what might intentionally or unintentionally affect the difficulty of the item. Ideally, more understanding of psychometric item statistics, especially if you are trying to control the variance in the difficulty of items generated from the same item model. And if you're using any type of proprietary or licensed item generation tools, interfaces, platforms, etc., you likely need some more specialized syntax for how to input item models into that tool. So why is this so important for this extra specialized training for item generation? First of all, because you're generating so many items, you can't review every single item. Doing so would take away the efficiencies in the first place from item generation. Therefore, any errors are more likely to go undetected in your generated items as compared to traditional item development where each item is reviewed individually. So it's kind of like finding a needle in a haystack, but you may not even know if an error exists in an item. Also, you might have content issues or alignment issues that could go undetected from types of automated checks. So even if you are implementing automated checks on the generated items to do things like ensure no keys are duplicated, items that look okay at first glance according to automated procedures might actually have significant alignment issues. So I'm going to go over 3 things to think about when training subject matter experts, which I will elaborate on in the following slides. But they are to include the SMEs in specifying the features in the item model, to help SMEs develop programmatic thinking, regardless of the content area that they are writing the item models in, and like all things, practice. You can never get enough practice. So the first one includes involving SMEs in the feature specification. The features are what components of the item can vary and may affect difficulty intentionally or unintentionally. And the guiding question here for the SMEs to discuss is, when looking at items within the same standard, how do those items differ in terms of their features, and how do those features relate to difficulty? So one thing to help guide this conversation can be to make a ordered item booklet of items within the same standard, ordered from easiest to most difficult, and look at examples of those items and talk about, first of all, what their features are and how difficulty might vary by switching the features. So here's an example of a math item. I'm using math examples because that's my area, but this really applies to any kind of content area you're working in. So if we think about what are the features of this item, and SMEs get really passionate about this, so it's a fun exercise. Some things that come to mind here are, this item uses function notation, so it has that f of x in the table versus y, so that's a step up. I also noticed that the values in the x increase by 1 consistently in the table. There's no real life context here. It's a purely mathematical context. There's some vocabulary such as average rate of change, and then also considering the types of numbers. So integers, but including negative values, and there is a fraction distractor. So having these types of discussions helps SMEs identify what features they should account for when they're writing their item models, whether you are intentionally wanting to vary a feature or hold it constant, and it can help create consistency and more precise predicted difficulties. The second consideration is to think about fostering programmatic thinking. So if you're working with math, your subject matter experts may already have some background in a little bit of programming, especially if they took at least one computer science class. Other areas might not have that type of background knowledge, but there are a ton of freely available, short programming courses online just to help people understand what it takes to tell a computer to do something exactly. How can this item model be written in a way that a computer can produce items from it? You can also have people use Excel to play around with making item models, whether it's formulas or taking things from lists and swapping them around. That's a easy tool that we all have with no investment. My personal favorite is to tinker with item generation tools. So if your testing organization does have some type of proprietary or licensed tool, it's super fun and helpful to get the SMEs in there just playing with things. We do have a tool at Edmentum, and here's an example of the first item I ever put in it. So I was just adding two numbers together, and looking at this, you might think, oh, this is a absolute value item, but in actuality, it's absolute value bars in our particular tool are how the tool knows that it's a value that can be substituted with a range. So this tool also allows you to generate as many sample items as you want, so I can immediately get the feedback on my item model by looking at the generated items and then tweak the item model accordingly. It's also helpful to try doing some of this manually. So looking at an item model and then manually practicing what the generated items would look like. This helps people understand what it takes in terms of how specific the item model has to be to get to a generated item. The third thing to consider, like anything, is that you can never get enough practice. So once you actually have tinkered and played around, when you are ready to start writing real operational item models, you can practice by writing examples generated from that model, similar to what I was just talking about, but focusing on the extremes and midpoints of your constraints. So I'll give a math example here again, just adding two numbers together, X and Y, and so those are the values that are allowed to vary. And I've specified here that they can range from 10 to 100. So if I think about what items would be generated from this template as I'm writing the item model, here are three possible cases. So at the low end of my constraints, an example is 11 plus 11. Then I can choose some midpoints, 55 and 42 or so. And at the high end, 88 and 94. You can also choose something at the low end and something at the high end, but any kinds of combinations of the extremes and the midpoints. So then when I see these example items, it's very clear that 11 and plus 11 is a lot easier than 88 plus 94. And although I didn't show a standard that this is intended to align to, I would guess that these three items do not actually align to the same standard. So therefore, I can change the constraints as needed to make sure that the alignment does stay intact. And as SMEs do this more and more, they will it'll become more automatic. They won't have to write sample items for every item model necessarily. They'll start to more naturally think through all the permutations and develop that sort of crystal ball of what is the universe of items that this item model can generate. Peer review and feedback is also really helpful. So looking at other people's item models and seeing if they make sense, and giving peer feedback just like in traditional item writing. And then if you are fortunate to get to a point where you have field tested multiple items through the item generation process, having SMEs involved in that data review conversation. So looking at the data from all items generated from the same model and seeing what is the variance of item difficulty and is that what was intended, can help SMEs understand how subtle differences in your item model and generated items can affect difficulty. So in conclusion, yep, writing item models is hard. It's a lot harder than writing traditional items one at a time. You do have to think through all the possible combinations. This will require additional training, feedback, and support for SMEs, but it's going to be worth it because that item model is your starting point for all these potentially thousands of items where you're not going to look at each one individually. So you don't know what you don't know in terms of what errors could be out there. So it's really important that the item model is very solid. So that's it for me today. Thank you so much for your time.
Thanks, Audra. Okay, Isaac, you want to try it again?
I'll try it again.
Okay.
Why don't you have the next person go?
Okay,
Rick?
I will do mine then. Okay, so I'm Rick Lecht from the University of North Carolina at Greensboro. And so I want to talk about a specific type of challenge of principled item design, at least as I've been dealing with it. I mean, if I actually wanted to spend time, we could talk about any of these things that are coming up, the lack of specificity of content, people that go hunting for difficulty drivers, QC of the task models, the exchangeability or isomorphism of AIG, et cetera. And I'm going to talk about parts of these, but none of these in specific. Now, one of the things that sort of drives me on this is a very simple thing of, you know, all these things I put on the screen here are pretty old technology by today's standards, typewriters, old Apple computers, rotary dial telephones, transistor radios, but why are we still designing and writing and pilot testing items like we did 50 years ago? I mean, I just find that phenomenal that we're that far behind the curve in terms of development. So the corollary is, can we actually borrow things from engineering design, industrial engineering design, manufacturing production, gaming theories, cognitive perspectives on memory and learning, and really help to create this notion of isomorphic or fully exchangeable item families by design, not just by happenstance or chance. So I look at it as something I call assessment engineering, which is a way to do assessment of the evidence-centered design. But the idea is that I don't think content is the same across the scale, and Audra alluded to that sometimes the complexity of numbers change or the skills, et cetera, and so we try to represent that. That means that incremental task difficulty is not just a statistical outcome, it's something that we can design, that we can make happen. And so, you know, for me, I really want to focus on the complexity of tasks because that's what we can change. I can't control what examinees bring to the task. I can certainly control to some sense, in some sense, the population I'm dealing with, but not what they bring to it. But I can control the challenges much like I would do, and I'm showing equalizers, et cetera, down at the bottom. I don't know if we're quite there yet, but I think we're getting close. So, you know, and this is sort of the point we start with. We always think of multiple choice items as being a fairly simplistic thing, but you saw this in Susan's presentation, that you can bring, actually chart it out as the initial problem considerations, and then they restructure the information or do something, generate some representation, maybe reevaluate hypotheses, and finally answer it. So there's actually a timeline, and we can control how those challenges appear along that timeline. Now, this isn't new. Game designers have been doing this for some time. I enjoy reading their things. They actually think about a plan for how they can put the complexity into the design of the game, the challenge encounters, the difficulty levels, how much time or distance it takes up, and the duration of the challenge itself. Is it sustained challenge or something that's instantaneous they have to respond to? So again, it's using these ideas of principled design. And again, these, we call these spark lines where the activity actually takes place. So the content itself was something I naively didn't really think about, but content really does vary in complexity, or other times it's invariant. So we have to think about everything as ordered complexity. Content, the presentation of the content, the skills involved, resources, tools, etc. Everything has a level of complexity, hopefully by design. So really what we think about is item difficulty modeling, and there's been a number of studies on that. We've had a few dissertations. I actually like to think of it as task model task model difficulty. And so we really want to get to the point that the specification is there. Can we, however, engineer the difficulties of the items like we would manufacturing instances of applying industrial engineering principles? I like to think we can get there if we spend the time to do it. It's not easy, it's hard. Now, I thought I'd insert here a nice little recipe for banana bread if you haven't had that, and send this to send me a note if you want to get a copy of this. But the point is, we have recipes on how to bake things, and so the question is, for a science item, could I actually take and do the same thing of getting the ingredients, of putting them together, preparation instructions, and then build that sort of item model or that task model from that standpoint? Okay. The problem is, what are the ingredients? And so I think that's one of the things that's motivated this whole session. Is I think a number of us have been interested in that for some time. I don't always deal with just the math items, but more complex things. I've been looking into something I think of as complexity design layers. And what these are is basically task constructs, things that we can actually measure, that we can actually derive in certain ways, and then by deriving them, actually manipulate them from simple to complex. So we can modify the declarative components, procedural aspects, or the content itself, depth of content required in order to develop it. And this just gives you sort of a depiction of how these layers fold in. Some may start out in the beginning and actually eventually go away, and other ones emerge along the way. And so being a sort of academician, I created labels for it, but the point is, we have to come up with what is this progression from simple to complex along the left. Now, two things I've been dealing with here is one is what I call derived complexity covariates. This is using things like text analytics, using natural language processing. We can even get to a point of using some machine learning options in order to actually predict some of these things. I mean, why have people trying to predict the difficulty of text when we can derive, run a product like Cometrics and get 106 indicators in a few seconds? I've also been trying to do some things lately with image complexity indicators to actually get at the depth of different images, whether it's an X-ray or something that you'd show in a math problem. And again, it's ways to represent the complexity either of the text itself, but again, things you can do automated. Now, one of the things that I realized is that that only accounts for some of it. When we've looked at some of the best studies I've seen out on this type of thing, using machine learning techniques or other techniques to try to get to these covariates, it's very difficult to get much beyond correlations of about 0.5 if you're just mining the existing data, trying to find out what are the hidden difficulty drivers. So I actually went back to the work by Kirsch and Mosenthal with document literacy over at ETS in the 1980s, and they had built a type of grammar for this. And so what I've done is try to say, well, what if we create this notion of complexity scoring protocols, literally a rating sheet that SMEs use to rate the complexity of things that I can't otherwise compute or get in an easy fashion. The nice thing about that is I can actually apply some of the typical score QC that we do when we apply it to human scoring of examinees, essays, or other things. So again, this is what it sort of looks like, and I'll show you an example of the study we did in a minute, but they would actually do this type of thing and could do it in about 2 minutes per item. You can have several raters doing it. You can look at inter-rater consistency, etc., and get to a point where they can rate quite a few different features of the items, and those become either an average or individual for a rater, the complexity indicators of these different features, these CDLs. Now, one of the things I learned early on is get rid of the labels. You know, we all like the things like Bloom's taxonomy or wording from Depth of Knowledge, Norm Webb's work, but the simple point is that we want to know what makes it from very simple to a little bit more complex to very complex. So I found numbers actually work far better to represent that than actually having people put these items into bins or think of them that way. Now, this is what it starts looking like. At the top, you can see all these complexity layers. There's no limit to this. I think I saw on Susan's graph, you know, she had 33 factors. You can have as many features as you want, and with machine learning that could get into the thousands if you wanted. You want to try to look at reducing them in certain ways. Now there's also the derivative complexity covariates, and these are things that I got from programs like Cometrics I mentioned that does the text analysis. Now, without going through a lot of this study, the details, we did an empirical study working with a company, a licensing exam that looked at biostats items. And fortunately, I had 3 really smart doctoral students who worked with me on this, and they had enough training in advanced stat that they were actually able to function as the SMEs in the study. And we spent quite a bit of time just trying to do a feasibility study. They each took on 3 training sets and 3 validation sets, and then actually served as each other's cross validation. So everyone did all 48 items in the end. And you can get a sense of the different content here, the things we see in stat, a few things from biostat like odds ratios, hazard ratios, sensitivity, and specificity. The items were balanced as best we could for difficulty of the item sets, and they did the rating. Now, they were actually looking for things like the concreteness of elements, key elements in the problem, connections between the stem and distractor. That comes from Kirsch and Mosenthal's type of study. I'm not going to, again, go through all the data here. These were basically the 12 complexity levels we got out. So there were a couple things related to the complexity of the content, but then also some declarative things, the way the ideas were appearing, information density, explicitness of ideas, and then the types of skills that examinees would need to solve the problem. I've also been exploring ways that we can look at graphically depicting the given items. These vertical lines are one item, how they progress across the levels, so you can actually see not only are you getting kind of a consistency in the level of the items, these are 8 items showing based on p-values, but you can also see is your level, like procedural skill, is really forming just 2 pockets or two clusters of items there, so it may not be discriminating that well. We are also able to get reliability here. Interesting enough, the first set was where we got the where they did their initial training, the least reliability, but it still wasn't bad. By the time we were done with it, got high degrees of interconsistency or inter-rater consistency in their ratings for the CSP. Now, initially, we didn't, we got some modest correlations for just the CSP readings. Then did some things with the Cometrics indicators, and again came down to a set of indicators here that we reduced down. And again, the R squareds weren't too bad. Again, it's only 48 items. It was an exploratory study in some ways. But when, as Susan had mentioned, when we put it together, here's where we're now getting R squareds near 0.88. And so we can actually get to a point, I believe, where we can actually control these components, both these cognitive or complexity design layers, and manipulate them in systematic ways. And it may not just be surface features. It's actually ways that we can see how manipulating, for example, lexical complexity or complexity of items can actually drive the piece. So together it gets back to this notion of kind of the notion of the CDLs, the complexity design layers, and these derived complexity components actually mapping out to a task model. And then the idea would be you'd use the task model to generate your item models and be able to create these item families from that. So I'm going to end at that point, and then I will stop share and see if Isaac, you back in? Let's see if he can get in. Okay. Matthias, why don't you just go ahead then, okay? You have to unmute too.
Ray, can you have Erin call me?
Hi, Isaac. Just hold on 1 second.
Or write to me?
Okay.
Okay, can you see?
Yes.
Okay, good. Yeah, so the next talk is about something that essentially does something not completely different, but tries to get at the idea of automated item generation using a very different set of tools. So I'm going to talk about deep learning approaches to automated item generation, and I will start with a few notes on where this came from. So AI or neural networks are really not a new idea. So there has been early work by Frank Rosenblatt in 1958 and later on perceptrons. Those were pretty simple networks, obviously, given the computer technology back then. But this goes back quite some time. What we're using today has its roots in perceptron and other types of developments. In testing, as early as 1987, there was a volume actually put together at ETS about AI in testing. So all these ideas are actually have been around for quite some time and have been evolving over the years, as we've seen in the last few talks as well. So it's getting more and more sophisticated. However, there's also this hype cycle, certainly. So we've heard that everybody's talking about machine learning, AI, etc. But very often when we then get down to the basics and try to predict something, we are still using models that we all know and love. And that changes only when we are venturing into things that are really hard to disentangle and to understand. When we are willing to actually go into areas where we are using models that you can't really explain well, that are really way too big to fully understand. But in terms of predicting things, we saw LLTM, we saw regression. I think the Kirsch-Mosenthal also used something like that. But once we try to actually generate stuff based on essentially learning from huge amounts of data, we have to go way beyond that. So what I tried a couple of years already ago was to play with recurrent neural networks or deep learning approaches and to build items that way. Essentially, yeah, you could almost joke that I try to do automated item generation without any principles, just by learning from a lot of data. And what came out is something that I would like to present now. The idea is, of course, we want cost savings, etc. We want to use automated item generations to make the task easy. And we all know that it's something that is still a challenge. You still have to train people. But what if we could do without that? We could just learn from existing items instead of going through all these steps with item models and training people to write them, etc., and analyzing everything in very detailed ways. So essentially, the basic idea is to get around all these steps by just having the AI or the deep learning approaches do all that work. It works quite well. We've seen in terms of more traditional approaches to automated item generation. There are a lot of other studies that we learned about today already. Here's another example. So even AI conferences have this kind of presentation. So I'm just showing it here to say, well, this also happens in other areas, not only in measurement and psychometrics conferences. So people look at this kind of stuff in many different fields. At the same time, you also have AI-based automated item generation, which still is based on item models. You can click through all the links that I'm providing. I think we're probably sharing the slides at some point. Or you can just jot it down here, question generator from Wolfram Alpha or the AIG from Cafe Lab. It's not Kofifi Lab. But yeah, there are item models. They are essentially filled with values based on training something, some models, some deep learning, maybe, I'm not sure, some machine learning algorithm. So what did I try to do? We would like to use deep learning, and I'm not going to go into much detail, trying to train a neural network to make items, essentially. There's a lot of lore and empirical knowledge about how to train those networks, because again, they can't really fully be understood. Even the estimation methods that we might call them, or the training methods, are also just an empirical way of somehow optimizing a network. So it's not fully an exact science. There's a lot of experience and trying out and adjusting the different estimation or training methods to do the right thing, or hopefully something that's useful. They are being used in computer vision. The lucky ones among you who own a car that has a self-driving chip in it might actually know that or have seen it somewhere on the web. There are language models that try to find synonyms, that try to answer questions, etc. There are sequence models that actually then give you some idea about how characters are put together to form words and then to form sentences, etc. So there's image classification, there's image captioning, question answering, question summarizing texts, and all that kind of standards applications. So why not automated item generation? In standard cases or in early cases, you have something like a neural network that essentially gets an input and an output and learns based on a supervised training set where you know the output, you know the input. There are also unsupervised neural networks that have striking similarities to clustering and classification methods that we all know and love. But mainly the approaches that you see in the news are supervised learning. However, these have more or less a fixed input and a fixed output, and it's like an image on one side, a classification on the other side, or some other form of prediction that you're trying to do. And you might have some hidden layers, but usually it's nothing super exciting. It's like a very complex factor analyzer, regression model, something like that, that produces high-dimensional output that you then interpret as text or classifications or what have you. Slightly different are recurrent neural networks. They try to do something else. They try to actually take sequences as input. They try to build up something like a memory. And they are not just input, intermediate, or hidden layer output thing. They have multiple hidden layers that are ordered in sequence, and they have an input and an output. And the output is more or less also the input. So you have a sequence x1, x2, x whatever, t plus 1. And at the same time, you have the input being just the previous value, so that you essentially try to predict what comes next based on the sequence of all the previous values. You can look at that as a conditional probability model. People try to model it that way, but these networks are just way too big to actually write down any equations, I would say, or even understand what is happening within those cells, because they have memory kind of feedback circles, etc. So this is a very simplified description of all that. So what did we do? We're trying essentially to use a generative language model based on this recurrent networks. And it's essentially, it looks like a no-brainer because those things are being used in text generation. You can find on the web all kinds of applications that are varying in quality. The problem with that is they usually take a lot of text, and I didn't have a lot of text. So I'm using a tool provided by Google. That's not so important here. Let's just skip it in terms of time. I can talk a lot about that later in questions if there are. What I did was I'm using one of these recurrent neural networks, essentially in a character-based language model, and I'm using open source items to generate new personality items. These items can be found obviously online. Many of you might know this database. There are about 3,500 items, personality type, and it actually works. So these are the items that I tried out in an empirical study, and half of them, I think the ones with the one, have been generated by the network. The other half don't have a one here, are actually items that appeared somewhere in the data. So I mixed them up. They're from a 5-factor inventory largely. So all these IPIP items are from the big 5 inventory. I think I might have tried a few other scales that I might have added, but mainly the majority of all the items came from the 5-factor model. So what happened? That's really the interesting question here. Do we know that these are good? How do we know that? Basic idea was simply to test them out. And again, the internet is helpful. $87.50 later, about 2.5 hours later, I tried out the items with about 300 respondents using Amazon Turk. About half of the items were generated by this neural network. The rest were existing items, published, open source items from 5-factor inventories. And when I looked at the factor structure that I got and the loadings, that didn't tell me any difference. When I looked at the factor structure of this 43 inventory of something test, it's reasonable to say it's something between whatever 4, 5, and 6 factors. So who knows with a small sample. So it worked reasonably well. The items kind of make sense. You can actually kind of guess which personality factor they belong to. So it was sort of okay-ish. So pretty promising actually. So yeah, maybe we can get better, have GANs to check the generated items, to actually select them automatically. But yeah, time flies. A year later, those networks were much more powerful. There was a network published called GPT-2. There were other networks. They usually go by the label transformer networks, and because I watched a lot of transformer movies with my son, I came up with this title. So we are like, we train those transformers. So a year later, I actually used a much bigger network, and I didn't train it only on 3,500 items, but I was working at NBME at that point, and I tried somehow to contribute to the idea that, well, we need a lot of medical licensing items, and can we actually do that automatically? So there were some tryouts with more traditional methods, and I thought, well, maybe give it a shot. So I used this GPT-2 transformer model and trained it a lot. These are really very large language models. I used a small to medium version with 345 million parameters, which is an incredible amount of parameters for anybody who estimates anything in psychometrics or educational measurement. So they just handle those parameters as if that's nothing, because they're using training methods that don't really look for a global maximum. They just try to optimize so that you get to some steady state or some stable thing. I used about 4 gigabytes of text taken from open access papers from PubMed, because I couldn't use, obviously, all the very secret and very secure medical licensing items just to throw them into a network and then publish about that. So I used medical text and thought, well, there's enough stuff in it that looks like a medical vignette. So they have case descriptions, they have descriptions of symptoms, etc. But I couldn't train it fully. Those big models, you usually get like a used car. You get a model that is already pre-trained, so it has a lot of miles on it. Usually something like Wikipedia is being used to train this stuff. And then you retrain the model with additional data. In my case, all I could find from medical papers that were open access, and the texts are fully available online that you simply can download and then pass into something that can be trained in a neural network. And that was even more successful. So I didn't show you here the stuff that is in the paper, but you get reasonably good vignettes, which are case descriptions. If you start a model prompt, so you start the model by giving it this sequence, so what are the most common side effects of blah, 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 then you will get answers. You will get an answer. You might get 1 or 2 or 5 answers, depending on where the network starts, and some random starting values. And you get something that is more or less meaningful. So in the worst case, you can use this as bad distractors, and you can throw it at somebody and can see whether they can actually use it as something they might want to improve, and then make good distractors out of that. Again, my model was huge, 340, 50 million parameters, but it was a small model compared to what's actually being developed commercially by OpenAI and Google and what have you. I was able to run it on an beefed up workstation that you can put together in your home. It's maybe a glorified gaming desktop would work. So you can run those smaller models. Otherwise, you can run this on Amazon Web Services and retrain, and probably get something that is much better now, because again, this was 99. Now we have the 2000s, and in 99 we had the large model was 1.5 billion parameters. I used the smaller or medium one with a quarter of that. In 2020, they published GPT-3 with the incredible number of 175 billion parameters, and everybody's writing about that now. The Guardian published a paper written by this thing. There are papers on, obviously, the limits and fake claims about this network. There are ways to test whether this thing actually can answer reasonably. There are assumptions about how to retrain this. So somebody trained it with recipes. People trained it to do whatever patent applications and generate ideas. But again, you also see articles that are really important that talk about the limits of this model. This model still doesn't know anything. It's just generating text based on input that you give it. But it's as smart as actually producing generated output in a programming language, or it can spontaneously translate stuff because it was trained more or less on all of the World Wide Web in so and so many languages. So if you give it a French sentence and say, translate this, these huge models are better than many machine translation models that we used a couple of years back. So if you compare them in standard things they haven't even been trained on, we call this a one-shot training or one-shot kind of trial. They can actually do many things that you wouldn't expect them to do because they haven't been specifically trained on. So my assumption is in a few years, we get something that is actually useful, that might actually be so good that you would just have, humans will either select those items, or you will have another network that actually checks those items that are generated against items that have been written by humans and have been vetted in terms of quality and adherence to standards, adherence to all kinds of constraints. So you might actually be able to use then those adversarial networks or other technologies to select from the model output and select automatically generated content, say, for example, for reading passages or something like that. And I guess I'm done.
Okay, thank you. Okay, Isaac.
Rick, do you have the slides?
Huh?
I
Oh,
sent them
here.
to you.
Oh, let me pop them up then. I didn't look back. We're going to do this the old-fashioned way then.
I'm going to do a very abbreviated thing because we have to be here out at 6 and we want to hear what our discussant has to say.
Okay, let me get Isaac's slides up here. Oh, a second, folks. My system's not. Let me close some stuff out here.
Is my screen visible?
Yep.
Yeah.
It is?
Okay, well, go ahead then. If you're, yeah,
How
yours
about
is showing, Isaac.
how
Yeah,
about
you're showing. Yeah.
It's working?
Yep.
Okay, very briefly, because we're running late here, I just want to say very few things here. Especially now that there's so many AIG projects going around, I want to talk about 3 criteria that we should be keeping in mind as these projects evolve. One is the idea of construct representation, which I will briefly illustrate with difficulty modeling. Construct preservation, something I haven't heard too many people talk about. And then operational efficiency, which was mentioned by some of the previous presenters. So I'm just going to read one slide of the construct representation idea because, again, we don't have enough time. Susan didn't mention it, but this is her idea from back in the 1980s, and I think it's a very fundamental idea. It's part of construct validity, and the essence of construct representation is this notion of knowing exactly what makes the items harder or easier. And so if you know that, you can then generate items with known difficulty and so forth. And I think this is a fundamental, it's fundamental in many ways. The idea, I see it reflected in other sciences. I'm showing here on the screen this last statement, presumably that very famous physicist Richard Feynman had on his board shortly before he died. And he says here, what I cannot create, I do not understand. So this to me is essentially construct representation when we apply that idea to test development. I've seen that same idea also in cell biology, where they're thinking, as the quote says here, talking about understanding and even possibly creating cells with certain functions. So that's the idea of construct representation. Any AIG project should be informed and have that as the foundation, because some of the other benefits of AIG may not materialize otherwise. So I was going to talk about some of my studies here, but in the interest of time, I'm going to go to the next larger topic, which is construct preservation. And I have a quote here from Lee Cronbach, 1980, where he says validation is not just about doing the validity once. You need to maintain that validation as different threats to validity come up. And this is why I talk about the idea of construct preservation. How does AIE relate to construct preservation? Well, a common problem in test development is that there are not enough items of a certain difficulty, and so you tend to use those items that you have too much, and therefore you overexpose them, creating security problems. So one way to avoid that is with AIG, but it's an AIG informed by different approaches to assessment design, like ECD, like also assessment engineering, which Rick mentioned, also the Mark Wilson's BEAR framework. There's many things. What I like about this particular thing that I think this is from Rick is that if you find items in one range of difficulty that are in short supply, you can backtrack and see how you can make more of that item type. So more of those items, I should say. So that assessment, construct representation aided by assessment engineering as deployed in AIG. And finally, I want to mention operational efficiency. And mention everybody has been bringing up the developments in AI, and this is another example of that. In AI, they talk about methods for automated question answering. And the most famous example of that is IBM Watson, which won the beat other human contestants in Jeopardy. So we can use some of that technology. Well, again, let me skip some of these things to do well, several things. One of which I'm calling item critiquing. If we have an automated model that can answer questions that we submit to it, we can, by, in a sense, tracing the solution process of that answering model, find out that certain items may be wrong. So if this model that presumably is able to answer all the items doesn't answer correctly some of the items, it could be because there's something wrong with the item, and therefore some subject matter expert should review it. So that would be some of the potential for this kinds of AI technologies applied to AIG, augmented with this idea of item critiquing. I want to quit here because I want to leave at least 10 minutes for Steve. So, so again, my point is that those three criteria, construct, representation, preservation, and so forth, are going to become increasingly important as more of these AIG projects come out, and we need to sort through them. The notion of cranking lots of items, to me, would be short-sighted. We would fail to learn about the construct. We would not leverage that effort to improve efficiency, etc. So anyway, that's my point. Sorry with all the troubles I had. Steve, you're on.
All right, good afternoon, everyone. I'm Steve Ferrara from Cognia. I've spent most of my career working mostly on state assessment programs, so my comments are obviously generated from my experience in those areas. Now, I'm going to share my screen, and I hope it's the right one. Okay, can you see my slides?
Yes.
Okay, good. Rick, rather than try to rush through and make comments on every one of the presentations, I'll make a couple of selected comments, and maybe I'll be able to leave a minute or two for a question or two, assuming you have them. So moving right along to provide some overview, you know, these 5 presentations, Susan's on cognitive design systems, Isaac's on validity argument framework and operational efficiency, which I do want to comment on. Audra's excellent work on training SMEs, principled item design for AIG, Rick's work, which I always follow, and the deep learning techniques for AIG that Matthias talked about. Together, I think they address 2 significant evolving developments in current testing practice. One is validity argumentation, not just as a thing we do at the end, but as the guide to build and operate testing programs. And the second big development is principled approaches to building and operating testing programs. And I use that acronym PADDY to be complete. It's principled assessment, design, development, and implementation. Going from soup to nuts is how I think about these things. All right, so let's see. The context that I use for thinking about these presentations, I start by reminding myself of what the goals of AIG are. I won't go over that because several of our presenters have already talking about that. But we're talking about programming items where we can know based on the empirical research we can determine the characteristics of items. And by characteristics, I mean their response demands. And I have 5 categories of response demands, and as well as their psychometric properties. And by the 5 categories of response demands I'm talking about are based on a literature review that I've been working on. I've reviewed over 100 item difficulty modeling studies and keep stumbling over more and more of them. So the 5 categories are item design, things like whether it's selected response, or constructed response, the role of the stimulus, and then content, cognitive, and linguistic demands. Variables in these 5 categories have been shown in large numbers of studies to predict item difficulty and discrimination. That's why I'm using it as a framework now. We know about the limits on the variety of items that we can produce, that people are able to produce so far using automated item generation. You guys are showing how we can, are illustrating how we can expand those horizons. And to that I say, wow, look at what we can do. We can't really do anything real yet, and look at how much is already accomplished. It's really pretty significant. So I'm going to skip to Isaac and then go to the end, and I'll have to apologize to Susan and Audra and Rick and Matthias because there's no time. The reason I want to talk about Isaac's framework is because he's broadened a framework of thinking about AIG onto item development, assessment, design and development, and operational efficiency using those 3 parts of the framework: construct representation, construct preservation, and operational efficiency. He's gone almost using PADI, principled assessment, design, development, and implementation. He's gone from the beginning and almost gets to the end being interpretation and use of the information that you get out of assessment. And in case you want to ask why reporting is not related to automated item generation, I turn your attention to the calibration stage in Rick's assessment engineering approach in something that I call item ALD alignment, where you need, if you're in a state assessment program and using achievement level descriptors to interpret performance, valid interpretation of that requires that the item response demands and the descriptors in each level of in the corresponding ALDs are aligned. So you get alignment like in this abstract representation in the first visual, where all of the response demands of all of these items are aligned with, oh, sorry, this is from a language testing program, from the advanced category. When you have misalignment is where you have items from other levels showing up aligned with the descriptor, items from one level showing up aligned on the scale, misaligned with a descriptor at another level. I mangled that, I apologize. I think the concept is might be discernible from what I said. So let me just finish by saying, thanks for all this creative and productive work from you guys. To me, it represents this progress that's being made in automated item generation and sticking to our guns about validity argumentation, valid interpretations and uses. And there are concepts and tools here that I think are adaptable and valuable for good old-fashioned human item authoring, or what Audra called, well, I think it was one item at a time authoring. I will make one bid here. I hope that someone actually tests the claim about assembling test forms using items from item families based on the parameters that are defined for that item family, and seeing how well the pre-equating works in forms assembly. And I hope that happens soon. It's a claim that several of you have made, and it needs to be tested and demonstrated so we can make sure that it really works. I'll stop there and say thanks again for inviting me to the body.
Okay, well, we got a minute or two, and thank you, Steve, for giving us a minute or two. But if anyone's got any pressing questions, I guess we could take probably one question or two.
Can you guys see me?
Yeah.
Yes.
Okay. Hi, my name is Vandana. I think a couple of you have come across and talked to you about item models and done some presentations on this. So what I wanted to say was that I was really intrigued with what we're presenting today. I'm gonna get my view a little better here. So we've done item models here at Cisco for some time. And the item models that Dr. Rick Lucent was presenting, I'm hoping I said that correct, are very in line to like the engineering style that we want to have when we're doing these item modeling. It's like the task difficulty modeling. And it encompasses models like Dr. Bajar has mentioned and Susan Emerson has mentioned that we're doing. So seeing this all and having actually the opportunity to speak to you all is actually, I think it's amazing. It's nice. And it's really evolving here that the last comment, Dr. Ferrer, that you had mentioned is like, hey, we want to see them on forms. If I have them on forms, how does that impact? How is that impacting us? And we're actually doing that right now. So we've had about 10,000 students responding to each child from an item family, you can say. And so we're in the process of trying to understand its impact to an overall form difficulty. We have lots of students that go through our program, but it was just like, well, how does that an item model make that impact? And really what we've seen from our previous studies that we've done and in-house studies we've done really comes down to that design, and that design at the beginning that we felt that it really comes out in our item statistics that we're seeing. The other thing that we're doing that I noticed that there was a rating scale that Dr. Rick was showing. So we have a rating scale that's a little more detailed at the STEM, at the diagram, and at the option level. And we're trying to we are trying to codify that to see how well that aligns to our item statistics that we're getting at the child level. So it's very interesting at all these different views, and then also trying to put the machine learning aspect, which I think is really cool. So we're in some of these ideas and processes that we've had, and we've done some Bayesian analysis here, but we've all we come down to, hey, it comes down to the design and well-designed thinking at the start, so that when we are generating these items, and we've generated 1,000 items because we have an automatic item generator from an item template, what does that look like?
Say somebody's planning a session for next year, I would include this presentation from
Yes,
Cisco.
definitely.
Sounds very interesting.
Yeah, and I am glad to hear you say, Vandana, that, again, at least for me, it starts with the design. It's hard to say if you have variation, from item difficulties that are intended, if you don't have a design that specifies what those were supposed to be like to start with. So
yeah, and that was really key, because we've had really good the ECD was really developed from the start. We had Bob Mislevy here to lead us on that work.
mm-hmm.
So when we created the item models, we shaped those item models to be very, at the gut, really, really well designed. And it's because it's IT, and on top of that, we're generating assessments that are going to be used worldwide. We were very concerned about, language, that English and in general, language that would be understood by everyone. Obviously we have translations that are happening, but those are getting, us getting concerned. And we do have items that are coming out great, item families that are coming out fantastic, but we do have a couple items like we would expect that behave differently. And it's because of the cognitive complexities that we didn't think through in some cases, that, hey, these two came together and that caused a problem, or there was a gap in curriculum that didn't address it.
Cool. Okay, well, I think we're probably at time here, a few minutes over. So I want to thank everyone who stayed on, and thank you, Matthias and Isaac and Audra and Susan for being part of this. So it was a great session. So thank you. Everyone have a good one.